Now that we've talked about the measure of center, let's look at the measure of spread, how far apart the data is. So the first one we're going to look at is called the range of a data set. The range of a data set is just the difference between the largest value and the smallest value. So if we had the average monthly temperatures for San Francisco, we would find the largest value, which is 63, minus the smallest value, which is 51. And so our range is 12. Well, range is easy to compute, but it's not often used. The reason is that it really only just looks at this big wide spread. Sometimes we want to be a little bit more detailed. So there's several other ways we can talk about the spread of the data. And when a data set has a small amount of spread, like these temperatures, most of the values will be close to the mean. When a data set has a really large amount of spread, more of the data values will be far from the mean. The variance is a measure of how far the values in a data set are from the mean on average. The variance is computed slightly different for populations and samples. So let's start with population variance. So let's say we're representing our values in the population with X's, and it's a population of size capital N. Now remember, this mu is the population mean. The population variance is represented with this symbol. This is a lowercase sigma, by the way. It's a weird symbol, but we'll go with it. The way we calculate the variance is we take the sum of the difference between each X value and the mean squared divided by the population size. So first we'd find the mean, then we'd find these differences, then square them, then add them up. So we're finding how far away each thing is from the mean. So in this circumstance, we would take each of the values. First off, we'd find our mean, we'd add them all together and divide by its 12. So my mean would be, I would take each of those values, add them up, I think I got them all. Yeah, okay, so 57.5. So to find the population variance by hand, it does take a little bit of work. I would have to find the difference of each of those from the mean and then square them. So I would be taking 51 minus 57.5 squared plus 54 minus 57.5 squared plus 55 minus 57.5 squared plus 56 minus 57.5 squared plus 58. So see, we're finding the difference between each value and the mean. Now to speed things along, which too late, writing all this down takes forever. Speeding it along, plus dot, 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 I would add all those up. And when I add all those up, I get a total of 169. And I'm going to divide that by 12. This is going to give me my population variance. And it gives me 14.083. Now let's look at sample variance. So when the data value comes from a sample rather than the entire population, we call the variance the sample variance. The procedure for computing the sample variance is a bit different from the one used to compute the population variance. First off, we're going to replace the symbol for mean with the symbol for sample mean. And instead of dividing by the population size, we're going to divide by the sample size minus 1. And I know that sounds kind of weird, and we'll talk about that in a second. Why do we do that? But what we would do is we would add them up, each value minus the mean squared, and then divide by n minus 1. So let's talk about why it's n minus 1. When computing the sample variance, we use the sample mean to compute the deviations. For the population variance, we use the population mean. It turns out that the deviations using the sample mean tend to be a bit smaller than the deviations using the population mean. If we were to divide by n, the sample size, the value will tend to be a bit smaller than the population variance. So there's a long mathematical process on why, but we'll go with it. So let's say I had these values from my sample. I would first find my sample mean. I would add them up and divide by 4 plus 6 plus 5 plus 4 plus 2. That's 24. Divided by 6. This one's a little bit easier for us to do. We're going to find the sample variance. Oh, by the way, the sample variance is a little s squared. Okay, so I would take each one, 3 minus 4 squared plus 4 minus 4 squared plus 6 minus 4 squared plus 5 minus 4 squared plus 4 minus 4 squared. This is a little bit easier for us to do by hand. Divided by, this is where it's interesting. We're going to do 6 minus 1. So, and in these calculators, you can actually do this all in one step. If you wanted to, you could do a fraction and then do 3 minus 4 squared plus, well, that's 0 squared. That one's easy. 6 minus, whoops, I forgot the minus. 6 minus 4 squared plus 5 minus 4 squared, which would be 1, plus 4 minus 4 squared, which is 0, plus 2 minus 4 squared, divided by 6 minus 1, which is 5, and it gives me a sample variance of 2. Now, we can also talk about the standard deviation. So the variance is computed using squared deviations. We're taking how far away something is from the mean and squaring it. So in most situations, it's better to use a measure spread that has the same units as the data. We really don't want to be talking about squared units of data. So to do this, we find the variance, and then we just take the square root of it. That's called the standard deviation. We're still talking about how far really things are from the mean, but now we're talking it a little bit closer in to what we're doing. So to find the sample standard deviation, we would take the square root of the sample variance. Population standard deviation, well, that's just the square root of my population variance. Now you say to yourself, oh my gosh, this takes forever. Well, we can actually do these in the calculator, and we'll look at that in a second. But if I knew my population variance, well, then the standard deviation would just be the square root of that. So I would just take the square root of 14.083, because that's squared. So we're going to take the square root of that. Oops. And we get 3.75. On the one with the batteries, we would take the square root of 2, which would be 1.414. I just happen to know that one, and so forth. Now we can also do this in the calculator. So I'm going to take that sample data that we had. Now I have stuff in my list, so I'm going to go up to the title and press the clear button, and that clears it out. Clear. Let's type in that data from the batteries. Let's see. It was doing this one since it's a little bit faster. 3, 4, 6, 5, 4, 2. When I go to my calculations, one variable statistics, this time I do not have a frequency table, so I'm going to clear that out. Again, it gives me my mean, which we got the same thing. And if we look down, see this SX 1.414? That's giving me this sample standard deviation. Now remember, these are calculated differently. This one would be the population standard deviation. So if this data had come from an entire population, I would choose the one with the lowercase sigma. But I can see that data right there. So it can be done in the calculator instead of having to do all those calculations by hand. Now let's recall that a statistic is resistant if its value is not affected much by extreme values, large or small. Standard deviation is not resistant, just like the mean is not resistant. Now we can also find the standard deviation on group data by putting it into L1 and the frequencies in L2. So we put the midpoint in for L1, the frequencies for L2, and we can actually get all this information when it's group data as well. So we're going to look at that real fast. So on this data, 0 to 50, my midpoint would be 25, 75, 125, 175, 225, and 275. So let's go in and do the group data. 25, 75, 125, 175. And notice this came from a sample, right? So we're talking about sample standard deviation, which in the calculator is represented with an SX. And it's 93.54. Now that's my standard deviation. What's nice is if it had asked me for the sample variance, that's S squared, right? Well, the calculator just finds the standard deviation, but I could take that, 93.54, and square it and get my variance. Now look at how big that variance is. This makes much more sense that in layman's terms of what we're doing. So we usually use the standard deviation when we're talking about how far apart something is from the mean.